So is my slide visible to all of you?
Yes, yes.
Okay. So good evening everyone. Today is the week 7 discussion of this course, deep learning, and myself Ayan Paul. I'm a PMRF research scholar from IIT Kharagpur, and I'm a PMRF TA for this course. My duties are I will discuss some of the theories, some of the questions, so that whenever you will be solving the assignment, you will not yeah, whenever you will be solving the questions, you will not feel a totally new concept. Okay. And about this course is deep learning. It was taken by Professor Sudarshan Iyengar, professor and head of the department of computer science and engineering, IIT Rohtak. Okay. So let's start the discussion. So today we will be discussing more about this training error, testing error, bias, variance, etc. Okay. So let's start with this concept of simple model versus complex model. Okay. So let's say that we have some points which follow a sinusoidal function. Okay, true fx. Okay, true fx or y. Okay, 1 minute. Yeah. Yeah, so let's say that we have some points that follow as sinusoidal function. Okay, that means the true function or y is a something sin x. Okay, something form of sin x. Okay, that is a true function. Okay, now what we are interested to fit two type of curves. Okay, one curve is a simpler curve. Okay, what the simple curve means is the predicted function it will have less number of parameters. So here the simple model, for the simple model I am taking a degree 1 polynomial. Okay, and degree 1 polynomial means a simple a straight line. Okay, and straight line means we have two parameter, one is w1 and w0. Second, we have a complex model. Okay, this is a complex model. So secondly, this is a complex model. Complex model, we have many number of parameters. Here it is a degree 25 model, so we will have 25 plus 1 or 26 number of parameters. Okay, so this is the thing. So again I am repeating, so I have many points. Okay, I have many points, and I know that it follows a true function, that is sinusoidal function or y I know. Okay, now with my neural network, what I will do, I will be predicting the output. Okay, I am saying that the predicted function now, I will compare two type of predicted function. One, if the predicted function is simple, that means it has a less number of parameters. Second, if the predicted function is complex, or it will have more number of parameters. So if it is simple, so I am taking a degree 1 simple predicted function, that is w1x plus w0. Okay, so it has only two parameters. Now for a complex model I am taking a degree 25 polynomial that has 25 plus 1, that is 26 number of parameters. Okay, so that is about the uh, a true relation of fx and predicted relations. Okay, again I am repeating, I have true relation, that is sinusoidal, and I have two predicted relation. One predicted relation is a simpler model, that is w1x plus w0, and second one predicted relation is a complex relation or complex function, that is a polynomial function of degree 25 with 26 number of parameters. Okay, and now I have just plotted it. Now this is a simple function. The line you have seen, this is a simple function. Okay, that is a straight line. The blue color curve you are seeing, this is a complex function. Okay, now note, in both the cases we are making as an assumption that y is related to x. We have no idea about the true relation. Yeah, we have idea that this true relation is some form of sinusoidal function. Now what we will do is we will take a training data set consisting of 100 data points. Okay, and now we will sample this 100 data points in 25 points in k number of set. That means in first set we will take 25 points, in next set also we will take 25 points. Similarly we will take many such training set, many such smaller training set to k number of times, and then we will plot the function. Now this is the, in this curve, this black line is the true sinusoidal function or true of true of fx. Okay, and this lines you are seeing with different colors, okay, straight lines with different color, this is a predicted function, and predicted function w1x plus w0. Now why there are so many lines? Because I have told you that we are taking 25 number of points with k times, that means many times. That is why we are getting so many number of lines. Okay, now what we are seeing, if I compare, what I am seeing is simple model trained on different samples of data do not differ much from each other. That means if I compare all this different color lines here, these are very closer to each other. Okay, so that means they are very close to each other. Second thing, if I compare with the true relation or the true fx or y, what I am seeing is this lines are very much far away from this sinusoidal curve. So this is my first observation. Now I will test with the second model, that is the degree 25 polynomial. Whenever I am testing with a degree 25 polynomial, what I am seeing is degree 25 polynomial is a complex model. What I am seeing is this complex predicted function is very much closer to the black line, that means the true function. Okay, and second thing, this predicted function, if I compare two different lines, like one blue line and one violet line or pink line, any line, these are very much far from each other. So this is my observation. So this is what we have learned in the first slide, that is the comparison of the simpler model and the complex model. So what we have learned, simple model fits well. Okay, simple model fits well, or it is very closer to the original function. Okay, original function or the true function. But in case of complex model fits well, and it is very much closer to the true function or this black color line. But in case of simpler model, it does not fit well, it is very far away from our sinusoidal function or the true function. Second observation, if I compare with the single model but with different training instances, what I am seeing is the for the simple model, this different color lines or this different color lines or a simple degree function, they are very closer to each other. But in case of complex function, they are very much far away from each other. So this is the difference between the simple model versus the complex model. So is there any doubt in this slide? Hello, am I audible?
Yes.
Yes, sir, you are audible and we understood very well.
Okay, okay. Now why we are explaining the, or why we are trying to explain the difference between, okay, someone is joining. Okay. So why we are trying to differentiate between a simple model versus a complex model? What is our idea? Our idea, we want to compare between the simple model and the complex model for the two terms, that is bias and variance. You must have heard about these terms very well, bias and variance. So what is this bias and variance? So again, this is our curve. Okay, and in this curve, this is red color line is the true function or simply fx, and this green color line is the predicted fx for a simpler model, that is why straight line. And this blue color curve is the predicted model for the is the average value of the predicted model for complex model, not the simple model but the complex model. Okay, so that is the curve. Again I am explaining, there are three curves here. So this red color curve is the true fx. Okay, true fx or true relation. Okay, someone is joining. Yeah. So this red color, this red color curve is the true model or fx. Okay, now there are two predicted model. One is the simple predicted model and one is the complex predicted model. This green color model or the green straight line is the average value of the simple predicted model, and this blue color line is the average value of the complex predicted model. Okay, now why we are taking average value? Because in the previous instances what we have done is we have taken so many training instances of 25 points, but we have taken the training instances to k times. That means 25 points we are taking, and we are taking for k number of times. That is why we have so many this different color curves. Okay, now what we are doing here is we are just doing the average of all this curve. Okay, if I do the average of all this curve, I will get a single green color line. Similarly, if I do the average of all these different color curves, I will get a this blue line. Okay, so that is why I am doing the average. Now this is the definition of bias. What is the definition of bias? Bias always compare between your expected value of the predicted function to the original function or the true model. Okay, so again I am telling, bias compute the difference between the expected value or the average value. Expected is nothing but the average value. What I was talking, that as we have taken so many trading instances, I am just doing the average. So that is why this expected value is nothing but take just the average. Okay, so bias is the difference between expected value of the predicted function minus the true function. Okay, now we have two kind of model. One is simple model and one is complex model. For simple model, what I am seeing is simple model. This is our simple model. Okay, so let me write s here, and this blue color line is our complex model. So for simple model, if I compare the simple model with the red color line, what I am experiencing is a simple model has a higher bias. Okay, but if I talk about the complex model has a lower bias. Okay, this is about bias. Okay, I think someone is joining. Okay, this is about bias. Okay, now we have a second parameter called variance. What variance do is, variance does not compare between the true function and the predicted function, but variance compare between different instances of your predicted function only, tested on different trained on different data. Okay, so that is the difference between bias and variance. Again I am repeating, if I talk about bias, so it is the difference between the true function and predicted function. But if I talk about variance, it is only the difference between the predicted function of predicted function it is only the difference between predicted function for different instances. So this is the variance. So in case of simple model, what we are seeing in this diagram is the lines are very much, or the predicted function are very much closer to each other. So that means simple model has less variance. But in this case, what we are seeing is all these different color lines are very much far away from each other. That means roughly speaking, we can say that this complex model has higher variance. So in short, if I tell about bias and variance, okay, there are two cases. One is simple and complex. Okay, simple and complex. So bias in case of simple model is large. Okay, simple model is large, complex model is less. But variance in case of simple model is less and complex model is large. So this is the difference in bias and variance. Again I am repeating, if I just talk about bias, so bias is the difference between your predicted function and the true function. But variance is only the difference between the predicted function that is trained for different instances of the data set. Okay, so that is the difference between bias and variance. Okay, so is this clear to all of you?
Yes, sir. Yes, sir.
Okay, now we will see about train and test error. Okay, now always what we do in a neural network, we divide the data set into two instances. One is the training instances and another is the test instances. Okay, so whenever our main aim is to compute the loss. What is the loss? Loss is the difference between the y value to the predicted value, or the true value to the predicted value. That is the loss. And what we are usually interested in mean square loss, so that is why we just squaring the loss. And as we can test it for different instances of the data set, that is why we are doing the expectation. Now there is a now proof is not here, and proof you can see in your that in your lecture note, because I don't have that time to show the proof. Now this MSE, or the loss, okay, loss is equal to, okay, someone is joining, okay, yeah. So this MSE, or the loss, it is equal to the square of bias plus variance plus some kind of irreducible error. Okay, this is the thing. Now what we are what we are what is our institution is, earlier we have seen this bias and variance. Okay, now we know this bias and variance both are error. Okay, if we have no error, then our bias and variance both should be 0. Okay, but bias and variance both comprises this error. So what is the mean square error? The mean square error is sum of this bias square plus variance plus some kind of irreducible error. Okay, that irreducible error we will see in some instance. Okay, now we have two kind of error. One is the train error and one is the test error. Now what is the train error and what is the test error? Now train error is first we are training our model with n training points. Okay, so the error that we will be getting here is our train error. Now we have m other data points for testing the model. So this is our test error. Test error will be 1 by m, and this thing is same. Okay, so this is there are two error. One is the train error and another one is the test error. Okay, now if you plot between the model complexity and the error, so this blue color line is the curve for the train error, and this red color line is the curve for the test error. Okay, now model complexity, according to model complexity, we know that if we have a smaller model complex or less model complexity, then we will be getting high bias. And if we are increasing the model complexity, or if we have a very much higher model complexity, then we will have high variance. Okay, so these are two areas of the curve. Now we have two things. One is the train error and one is the test error. This is the train error and this is the test error. Now when we will plot it, what we will see is the train error will always decrease. As we increase the model complexity, the train error will always decrease, and as we keep on increasing the model complexity, the train error will be ideally it will be going towards or tend to 0. Okay, but it is not in case of the test error. For test error, what we find out that test error initially decrease. Okay, and then it will reach a point at which the test error will be minimum, and then test error will again increase. Okay, so this is the difference between the train error and test error. Now if you will only see the training error, you will not get a clear picture of the result, because what can happen is, as you are increasing the model complexity, your train error will be very much uh, less, or may reach to 0. But when you will be testing your model for a different data instance, like if we are training with n data points, and then if we will test with m data point, what we will see is our test error is increasing. Okay, so this is the theory, or this is the plot of model complexity versus the error. So again I am repeating, we have two kind of error. One is the train error, that is the error on the train data set, and next is the test error, that is the error on the test data set. Okay, now now thing is, as we increase the model complexity, what happens is the train error will be reaching to 0. but that is not the case with test error. Test error initially it reaches to a minimum value and then again it increases. So if you are only interested in a train error, that will not give you a clear picture how your model will perform to the test data set. Okay, so that is the thing. What we are interested in, we are interested in finding this point at which our test error will be least. Okay, and this is again at some kind of trade off. Okay, because both error we cannot reduce to zero. Okay, so again we have to find a sweet spot at which the test error will be the test error will be minimum. Okay, so this is the institution, or this is the theory of the train versus the test error. Okay, so is it there so
Hello,
yeah, please.
sir.
Yeah, please.
Sir, you have said high bias and high variance.
Yeah.
So what that means, the error, this region shows error with high bias, and this region shows where the error will have high variance. Is
Yeah,
that the meaning?
high bias and high variance, it always it is related to what? Model complexity, right? So model
Ah,
complexity, if we have a very less model complexity, or if we have a simpler model, we will get a high bias. Okay,
yeah.
and if we have a complex model, we will get a high variance.
Ah,
Okay,
okay.
so this is
Okay,
the
now
thing.
we understand, sir.
Yeah,
Okay.
this is the thing. Now, now whatever we have discussed, it is regarding the train error versus the test error. Now we will see true error versus the model complexity. Okay, so the error is nothing but this is a true error. Now true error is related to model complexity. How true error is related, I am not going to the maths much, but true error, our error is always this. Okay, this is bias square plus variance plus some kind of irreducible error. If we talk about the true error and empirical error, so true error is related to empirical error plus some constant plus a covariance. Okay, and this I am talking about this test data, not the training data but the test data. Okay, now according to some kind of theorem called the Steen's lemma theory, Steen's lemma theory, this covariance part will be equal to this, and this is related to and this depends on this, that is del f xi by del yi. Okay, now del f xi, this is the predicted. Okay, this is the predicted del of predicted function divided by del of this true function. Okay, yi is your true function, this f predicted xi is your predicted function. Okay, now what this is telling is, as uh, this is telling is, as we have a complex model, whenever we will have a complex model, it will be more sensitive to change in observation. Okay, that means yeah, this true error will be empirical error plus small constant plus the model complexity. So this term is nothing but it is related to model complexity. So again I am repeating, this true error is empirical error plus some small constant plus it is related to model complexity. Why it is related to model complexity? Because we have this Steen's lemma equation or theory, whatever that converts your this part to this part. Okay, and this part, in this part we can see this. If we have a complex model, if we have a simple model, then this part will not if we just do some change in observation, this part will not change much. But as we have a complex model, this part will change much. Okay, so that is why this part, this true error is related to empirical error plus small constant, plus this part is nothing but it is related to model complexity. Okay, now if we see in this graph, okay, this yeah, this we are talking about this thing. Okay, we are talking about this thing, or the test error here. So test error, see, for this test error, we have this part. Okay, this part is nothing but your, this part is related to complexity. Okay, because as for this training error, our error is reducing to 0, but for our test error we will have a more error. Why? Because as model complexity increases, our test error is actually increasing. Okay, so this is related to something called as complexity term. Okay, so this complexity, earlier what we are interested, earlier we are interested in only the training error, so that is why we were doing the only we are only doing the optimization in this L theta. Okay, or just the this loss. But now what we will do is we will be we will be more interested in this complexity term also. So that is why we will do our we will do our back propagation in L, for this L theta, plus also for this complexity term. Okay, so that is why now we will do for this complexity term also. So yeah, so now this complexity term, as you have as you will recall it in the last lecture, we have introduced this complexity term in the last lecture also, in terms of this sigma. Earlier our loss was L theta. Okay, now what we are writing our loss is L theta plus sigma of theta, or whatever you call it. This is sigma of theta. Okay, sigma of theta. So that is why so that is the thing. This sigma theta is nothing but it always comes from your complexity factor. Okay, so this is the theory behind it. And now, if we can make this complexity factor by our own, earlier if we are only focused about this training data, we don't have any complexity factor. Okay, that is why training loss reduces to 0. But we know that we cannot judge our model by only this training error. So for test error, we have a complexity term. So to make this training error to the test error, what we will do is we will add some kind of complexity term, and this complexity term is the basis of all the regularization methods. Okay, so this is the theory behind it. Why we are doing regularization? In the last class also someone was asking that why we have added this sigma theta. So we have added this sigma theta for introducing a complexity in our training error, so that it will make a good approximation of our test error. Okay, so this is the theory behind it. Okay, so is it clear? Now we will see different form of regularization. Last class also we have discussed about regularization, but we have discussed completely in terms of autoencoders. Okay, now we will see in a more general aspects. So first we will have L2 regularization. Okay, we will also have L1 regularization also, we will have L2 regularization also. We do not use L1 regularization that much, because what L1 regularization does is it drives our weight to 0. Okay, what is the idea of regularization? Idea of regularization is increasing the you can say idea of regularization is to because we are dealing with neural network, so neural network has large number of parameters. Okay, now if we do the regularization process, it will earlier our weight can take the whole search space. Okay, so our weight can take any number of values. But if we do this regularization, we are restricting the weight to a certain boundary, so our weight will not get that freedom to that freedom to adjust, and our weight will not adjust much. So by that what will happen is, earlier our training error will be going to 0 completely. Now our training error will not reach 0 completely, because we are performing such kind of regularization. So this L2 regularization, what does it do is it limits the weight to a smaller value. We do not use L1 regularization, because L1 regularization, it reduces the weight completely to 0. After many instances, it reduces the weight completely to 0. But this is not in case of L2 regularization. That is why we generally use this L2 regularization. Okay, Now this is the formula. Earlier we have this only this loss, now we'll have loss plus this sigma theta. Okay, sigma theta, and this sigma theta or sigma w, as here we have only one parameter, that is w, so that is why sigma theta or sigma w. Okay, so let's write it as sigma w. So this is sigma w and this is plus alpha by 2, this something weight square. So earlier we have only this loss, the lw, now we have lw plus some sigma theta. Okay, lw plus sigma theta or sigma w, whatever. Okay, because here we have only one parameter w, so that is why I am writing w. Okay, this is the thing, and this is the regularization, that is alpha by 2, this sigma w is this alpha by 2 and w square. Okay, and earlier yeah, SGD5 we are interested. Okay, so let's leave this. Earlier we have only this. Okay, now as we are adding this, so we will have this as our updated weight. Earlier our updated weight was wt plus 1, that is equal to wt, okay, minus eta LWT, eta del LWT. Okay, del eta del, this is del, and LWT, WT. Okay, so earlier we have this. Now as we are introducing this alpha by 2 w square in the loss term, now it will be this minus eta alpha WT. So this is the change in our SGD rule or update rule. Okay, now if I show you by diagram, so earlier we have whenever we are not doing the regularization, earlier our optimum weight was w star, but as we have done the regularization, what we have done is we have restricted the weight. Now our weight w star is becoming w tilde. Okay, w tilde, now this is our weight, so we are, it's nothing doing but we are decreasing the weight. Okay, and after this L2 regularization, you can prove by equation and all, you can see in your this lecture notes how it is proved. So what does L2 regularization do is it perform some kind of this eigenvalue decomposition only. Okay, so eigenvalue decomposition, we have three steps in the eigenvalue decomposition. One, there is a rotation, then there is a translation, and then there is again a rotation. Okay, so ultimately you need not need to understand all this, you just need to understand this, that earlier we have a higher kind of weight, that is w star, or we have large weight. Now we are restricting our weight to w tilde. Okay, so by that we are doing the regularization. What is the meaning of regularization? We are restricting our weight to a certain boundary. Earlier our weight can take the entire search space and adjust by itself. Now we are restricting it to a certain boundary, or we are adding some constraint to the weight, so it cannot explode more than that. Okay, so that is L2 regularization. So this is the thing. Okay, so this is the thing. Now this is the second type of regularization. So we can also do the regularization by a technique called dataset augmentation. Okay, so earlier this dataset augmentation is a very popular technique in the case of CNN, or neural network for this image dataset. Okay, this is a popular thing. So our idea is we exploit the fact that certain transformation to the image do not change the label of the image. Like this is an example of our MNIST dataset. Okay, so MNIST dataset, it consists of I am not remembering the exact number. I think 75,000 image or something image of the handwritten digits. Okay, so this is the MNIST dataset, and this image is one of the image of this MNIST dataset. Now this image has this label 2 because 2 is written on it. Now the dataset augmentation, what it exploits the fact that certain transformation of the image do not change the label of the image. Like what type of transformation? If we just rotate the image by some degree, okay, still the label is still 2. If we again rotate with some other degree, again the label is 2. If we shift vertically, like earlier our image was right at the center. Now we are shifting vertically, like shifting up or down. Okay, so then also our label will not change. Shifting horizontally, like right or left. Okay, earlier our 2 was in the center, now I am just shifting it horizontally towards left or right, then also its label is not changed. Then I have just blurred the image. Earlier we have a clear image but blurred the image. Still 2 is visible, so our label has not changed. And then change some pixel, that means just we can add some color, etc. So by this, so we are doing all the operation. This operation is nothing but your augmentation. Okay, this is nothing but augmentation. All this operation together is known as augmentation. So we are exploiting the fact, even if we are doing the augmentation, the label of the image does not change. So so why we are doing this? We are doing this for creating more number of data. So in MNRT dataset we have many images, so we don't have this problem. But whenever you will be collecting real dataset, okay, like real images of apple, banana, or anything you want to capture, so what happens, the problem is you can't collect that number of images. Like if you need 10,000 images, 20,000 images, that much images you cannot collect. You will either collect like 1,000 images, not more than that. So what you can do is you can augment the data to have data with more number of images. Why we are augmenting the data? To have so that our neural network can learn better. Okay, so that is the idea. More data means better learning. So it works best for this image classification or object recognition tasks, and also it has been shown good progress in this speech recognition data, etc. Okay, but this is the idea. So again I am telling, what does we do in image augmentation? We from a smaller dataset, our idea is to create a large dataset so that the label does not change. How we can do? We can do with different type of transformation, like rotation, then shifting vertically, then blurring the image, adding some pixel, etc. We can do all this without changing the label of the image. Okay, so that is data augmentation. Why we are doing this? Because if our neural network will have more number of data, so it will learn better. So that is why this is a that is why by this we can our neural network can learn the better, or we can make the neural network learn better. Okay, so that is data augmentation. So any doubt in this? Why we are using this data augmentation? Okay. Now parameter sharing and time. So this we have discussed some part of it in the autoencoder also. So what happens is, as regularization, why we need this regularization thing is because we have our neural network have so many weights, so it overfits the data. That means it drives our training error to 0, but our test error is not 0, or our test error is more. Okay, so that is the problem. So the main problem, why it is so, because we have so many number of parameter. So our idea is parameter sharing and tiring. Our idea is, let's decrease the parameter. So how we can decrease the parameter? We cannot vanish the weight of a layer. That we cannot do. If we vanish the weight of a layer, what will happen is, we cannot forward propagate, or we cannot back propagate, or even we cannot compute the loss. So there are three process in our neural network. One, we just forward propagate to reach the output. Second, we compare the loss, and next we back propagate to calculate the we back propagate to adjust the weights. So these are the three process. Now if a layer does not have weight, so what will happen is, our neural network will not work, because we cannot our neural network would not be able to calculate the output, neither it will able to adjust the weight. So we cannot just vanish some parameter, that we cannot do. So what we can do is, we can share the parameters. Like for different layers, earlier, like I have 3 hidden layers, so for 3 hidden layers I have 3 set of weight. For this h1 I have 1 set of weight, this h2 I have 1 set of weight, and this h3 h2 I have 1 set of weight, and this h3 also I have 1 set of weight. So I have 3 different set of weights earlier. But now what I can do is I can do the parameter sharing. That means I can equalize the weight of h1 layer and h3 layer. Okay, so by that what I am doing is I am decreasing the number of parameters. Okay, so that is parameter sharing and time. We have also discussed this in the case of autoencoder also. So this is parameter sharing and time. Now another thing is adding noise to the input. We again have discussed in case of autoencoder. So earlier what is happening is we are taking the input as it is. Okay, but now what we will do is we will add some of the noise to the input, and before our hidden layer learns, it does not learn the raw. Okay, someone is joining. Yeah, before our hidden layer learns from the input, it will not learn from the raw input, rather it will learn from a noisy input. Because if it will learn from a learn from a this raw input, what will happen is it the model will not be generalizing well. That means it will drive our training error to zero, but whenever we will try it with the new data, the test error will not be zero, or the test error will come more. So that is the thing. That is why what we will do is we will add noise to the input. So now our hidden layer will not learn the raw input, but now the hidden layer will learn the noisy input. So this is adding noise to the input. Okay, now we can also add noise to the output. So whenever we were calculating loss, okay, so earlier what we are doing is we are calculating loss from the true output, or we are calculating loss from y. Now we will calculate loss from y star, means a noisy output. Okay, not the real output but a noisy output. So by this also we are just increasing our loss. We are not driving our training error to zero, or we are not driving our loss to zero. We are adding more to the loss. Okay, so earlier yeah, this whenever we are talking about this real output, that are hard targets. Okay, real output. But now what we will doing is we will be supplying some kind of noisy output, so that are soft targets. So this is the thing. So this slide, if I sum up, what we have learned is parameter sharing and tying. Parameter sharing and tying, why our model is model why our why we need to perform regularization is that training error reaches to zero, but this is not the case for the test error. Okay, so for that we are performing the regularization. The idea of regularization is earlier, because in neural network we have so many number of parameters. So as we have so many number of parameters, so our training error will be essentially zero, or our model will be trained in such a way that the weight will adjust itself and drive the training error to zero, because we have so many number of parameters. So it will learn and learn any training data, but whenever we will be supplying test data, it will give us more test error. Okay, so in parameter sharing, what we will do is, our idea is we have so many number of parameters. So if we can lessen the parameter, or we can vanish some of the parameter, our training error will not be driven to zero. But that we cannot do directly. Why we cannot do directly? Because if we just vanish some of the parameters or some of the weight, what will happen is we cannot perform this forward propagation, we cannot perform this calculate the loss, and we cannot perform this backward propagation, or our neural network will not function. So instead of that, what we will do is for two different layers, or two different hidden layers, or any two different layers, two or many different layers, what we will do is we will equalize the weight. As we equalize the weight, what will happen is we are now reducing the number of parameters. So that is parameter sharing. Next is adding noise to the input and output. So adding noise to the input, earlier our hidden layer is learning from the true representation of the input. Okay, but if we can provide some noise to the input, our hidden layer will learn from the noisy input, and then it will not drive the training error to 0. Similarly, adding noise to the output, earlier we were calculating loss from the true output, but now we will be calculating loss from the noisy output. So by that also we will ensure that our training loss would not drive to 0. Okay, so this is the thing. So is it clear to all of you? Oh, okay, now there is a method called early stopping. Okay, now what we are seeing here in the curve that we have discussed again and again, what we have seen here is, if we can what is our most optimum point? Most optimum point is the point at which our training sorry test error is minimum. Test error or validation error, whatever you tell, test error is minimum at that point. That is the optimum point. Okay, so if we can stop our training at that optimum point, so by that also we will ensure that our model will not overfit, or it will not drive the training error to 0. So that is the institution behind this early stopping. So what does early stopping do is, it track the validation error or the test error. It has a parameter called patience parameter. Okay, so what does this patience parameter do is, it checks the validation error always. Okay, and it ensures that if for the number of patients our validation error is not decreasing, okay, so it will stop the training at that point. Again I am telling, like our patience parameter is 2. Okay, so it will see our validation error is decreasing. Now for two instances, if it will see is, our validation error is not decreasing but increasing, rather increasing, so it will stop the training at that point only. So this will ensure that our training error will not drive to 0. So that is the thing. Okay, so this is about early stopping. Now again, as we are doing early stopping, what it will ensure is that there will be some parameter which are important parameters. Okay, so this del L theta by del W, or the gradient, okay, that will be small if the parameter is not important. Okay, and it will be large if the parameter is more important. Okay, so by that only it will update the weights. Okay, so it will ensure that if we are early stopping our training early, it will ensure that only important parameter will get proper update, but the parameters which are not that important, it will not get proper updates. So that is again a way of explaining the early stopping. Okay, we will do a question of early stopping also, so there also it will be more clear to you. Okay, now next thing is ensemble method or ensemble method. It is pronounced as ensemble method. Okay, so what does this ensemble method do is, ensemble method means if we are testing not on the basis of one model, but we are testing on the basis of many model, so what will happen is our average error will get reduced. Okay, the average test error will get reduced, because earlier we are only testing with only one model, so our average test error is large. But if we test on with many such type of models, what will happen is, it will do the average. So average is always lesser than single value, right? So that is the theory for this ensemble method. So ensemble means combine the output of different models to reduce the generalization error or the test error. The model can correspond to different classifiers. Okay, so now how the model can be made? I am telling that our model will we will test with different model. So how our model can be made? Our model can be made from different classifier. Means different neural network, you will apply different activation function and all, like that. So that you can do. Otherwise you can take the same neural network, and what you can do is you can adjust different hyperparameters, you can adjust different features, like your data will have different columns or different features. Now what we will do is, for the same neural network, one model you are training with a different number of features, and the model you will be training with different number of features. So that also you can do. Other thing is, you can use different samples of training data, same network, same hyper parameter, same feature, but for one model what you will do is you will provide a different set of data, next model you will provide different set of data. That also you can do. So that is how you can perform this ensemble method. Now ensemble method, whenever we are talking about the third point, that is different sample of the training data, there is a process known as bagging, or this the full form of it is bootstrap aggregating. So what is a bootstrap sample? Like, this is your container, okay, and you have 100 different, let's say, candies, okay. Now you need to take 20 candies at once, okay. So what you will do, you will take 20 candy, you will take then 80 left, then you will take 20 candy, 60 left, 20 candy, 40 left, like that, 20 candy, 20 left, and whenever you will take last 20 candy, your bag or your container will be empty. So this is normal sampling that we do. But in bootstrap sampling, what we do is we do the sampling with replacement. Okay, now what you will do is 20 candy you will take, you will make a model, then again you will put the 20 candy back to the bag, okay, and then again you will make the again you will take 20 candy, and again you will make a different model. So we are doing that is sampling only, but now what we are doing is we are doing sampling with replacement. So that type of sampling is known as bootstrap aggregating, okay, bootstrap aggregating, or short, this is a bagging, okay. So from a given dataset, construct multiple training sets. Okay, someone is joining. Yeah. So from a given dataset, construct multiple training sets by sampling with replacement. Yeah. So always what we do is bagging is, we do not do the normal sampling. We do sampling with replacement. So that is the idea of this bagging or this bootstrap aggregating. Okay. Now the error, that will be average error. Like, yeah, like now you have made n different type of, or k different type of models, okay. Now you need to test a test a separate data, okay. Now what you will do, which model you will use all the model and take the average of the prediction. So the average of the prediction will be, if we have k different model, then this will be the average of the prediction, and this is related to variance and covariance. Now what is this variance and covariance? Now as we are taking so many model, then our model will have some kind of variance and covariance, okay. Now this is the thing, the theory, you can say that if the errors of the model are independent or uncorrelated, then this c will be equal to 0, and we only will have v by k. That means the prediction divided by number of models that you are training. But if our errors have some connection, then we cannot completely ignore the covariance, so we have to take the covariance also. But whatever the idea of the ensemble method is, it will always give a less generalization error than the only a one model. Whenever you will be experimenting only with one model, your generalization error or the test error will always be greater than whenever you will be using this ensemble method. Because in ensemble method we are combining so many models and do the average prediction, so average will always be lesser than individual value. So this is the idea of the ensemble method, okay, or ensemble method. It is pronounced as ensemble method, okay. So this is the thing.
Sir, I have doubt.
Yeah, please.
Sir, actually, we have three here. You can see logistic regression, SVM, naive bias. We have three models,
Yeah,
and we take the average of the three output, and we give Y final
yeah, yeah,
in the diagram. So what I'm going to do is we compare with the true value
Yeah,
and find the error, we are going to update the weights.
yeah.
Then we will do it for individually for all large distribution model, SVM model, and naive bias like that.
Can you please repeat? I think I
No,
didn't
no, we
clearly hear.
update regularization. The weights we will change now.
No, what is our idea? Our idea is to reduce the test error, right? That is our idea.
Yes, yes, yes.
So
Yeah.
whenever you will be doing with only one model and you will
Uh,
predict the test error, that will always be more. But when you will do the average, like this by 3, our test error will always be less. So that this is the rough idea of this ensemble method. Okay.
okay, okay,
So
okay, okay.
our idea is to reduce the test error, so that we can do by different ensemble method we can do by different technique. One, we can use, like in the image we can use three different or n different models, and we can do the average of it, or n different classifiers. These are different classifier or different, you can say different activation function, that we can do that three completely different model, and then we can ensemble it, that you can do. Otherwise what you can do, you can just take one model and you can change the hyperparameter of the model and make different models, or you can what you can do, you can play with the features, like in your data you have many features. So one model you take the first 10 feature and the model you take the second 10 feature, like that also you can do. Or third, you can do this bagging or bootstrap aggregating. That means now you are training only a single model with single model with same hyperparameter, same feature, but this model will be trained with different training instances. Okay, and this training
Okay, okay.
instances are nothing but your bootstrap
See?
aggregating or bootstrap samples. Okay, so this is the thing.
Okay, I understood this one. Okay. Okay, sir.
So let's move on to the next thing, and this is the last thing, that is dropout. So typically the problem with the ensemble model is, if we train several it is computationally expensive. Okay, why? Because if we train several neural network having different architecture, obviously it will be expensive. Second thing, if we train multiple instances of the same network using different samples of the training data, that is also expensive, because we are adding different models to our calculation. So definitely it will take more compute, it will be more computationally expensive. So that is the limitation of what you call as this ensemble method. So to deal with this, we have this dropout technique. What does this dropout technique does is, it drop out some of the neurons of the hidden layer. Okay, simply in very simple definition I am telling, what it does, it focus on the hidden layer, not the input layer, not the output layer, but generally it focus on the hidden layer. And it, what it does, it thin the network. How it thin the network? It drop out some of the neurons, and when some of the neurons get dropped, the weights associated with it will also get dropped. Okay, so if we have n neurons in our like hidden layers, so number of ways in which we can do this thinning technique is 2 to the power n. Okay, this is maths, nothing, this is maths. So if this question might get come, so that is also, that is why this is important. So if you have n number of hidden neurons in the hidden layers, then you can perform this thinning in 2 to the power n ways. Okay, so this is the thing. Now this is an example of dropout that has been shown here. So what we have done is, in the first instance, like this is also some kind of ensemble only, right? But in this ensemble, earlier on all the ensemble methods that we are doing, it is becoming computationally expensive, because so many parameters again and again and again and again. But here what we are doing is, we are dropping some of the neurons. So as we are dropping some of the neurons, the parameters also vanished. Okay, so by that what we are doing, we are making this thinned neural networks. Okay, so as we are making the thin neural network, our computation cost actually reduces. So this is the theory of the dropout method. Okay, now there is a theory for this testing the dropout method. So Earlier during testing also what we are doing, we are just passing our test data set to each neural network and computing the output or computing the result. Now what can be done is the probability at which we are dropping this dropping the dropping the neuron, that probability we can multiply it with our weights, okay, with our weights of the full layer, okay, and then we can calculate the output. Okay, so by that only testing only one complete neural network, we can solve the problem of the computation. Okay, so this is the thing. So again I am repeating, let me repeat it again. Ensemble method, we have seen ensemble method and we are happy with it, but only difference with the ensemble method that it is computationally expensive. Why it is computationally expensive? As we are training several neural network having different architecture, and then we are training multiple instances of same network but with different set of data, so all this will make our computational expensive. So for to have a solution of this problem, okay, someone is joining. Okay, so to have a solution of this problem, we came out the idea of dropout. What in dropout we do is, we will again be solving our thing like an ensemble method only, means we will be again making so many thin network. But now as we are making a thin network, what okay, first thing, what is a thin network? Thin network means in the hidden layer we are just dropping some of the neurons, so that is a thin network. So what we are doing, we are making so many thin network. So earlier in ensemble method, what is happening is, whenever we are doing training, we have to training each neural network, the dense neural network again and again and again, so it is computationally expensive. Now as we are dropping some of the neuron of the hidden layer, what is happening is as we are dropping the neurons, so the weights associated with it also get dropped, so our parameter will be less than we are doing in the ensemble method. Second thing is, during testing, earlier in whenever we are doing testing of this ensemble method, what is happening is, we are passing the testing data instance to all the neural network, and then we are calculating the average value of it. Now we will not do it. Now we will take the whole neural network at once, and the probability at which our neurons were dropped, that probability we will be multiplying with the weights and calculate the results. So by that, unlike our ensemble method, we do not need to test our training data with different neural network. We will test our will test our data with only one large neural network. We will just modify it weight to the probability with which it will get dropped. So that is the thing. So by that we are solving the problem of computation of the ensemble method. So this is the dropout method. Okay, so this is the thing. So is it clear to all of you? Okay. So by this we will be moving to our question answer session. Okay, so our question will be answer of this week will be based on this bias variance, train test error, true error, model complexity, and different type of regularization. Okay, so this is the first question. So again, I will be expecting everyone to, I will show the question, I will expect everyone to guess the answer first, and then we will be discussing the answers. Okay, so first two question is based on this common data, and we have two different kind of model. One is f1 predicted, this hat is for predicted function. Okay, so f1 predicted x, that is w0 plus w1x, and f2 predicted x, that is w0 plus w1x square plus w2 x square, w4 x to the power 4 plus w5 x to the power 5. Okay, so this is the second model. So we have two kind of model. Now the first question is, which of the model has higher complexity? Okay, is it f1 predicted x, or is it f2 predicted x, or is it c? It is not possible to decide without knowing the true distribution of the data points in the data set. So any guesses for this? I hope it is clear.
I think B is the answer.
Yeah, b1, right?
It's have
Yeah,
to be.
yeah, exactly, b1. Why b1? Because it has more number of parameters. For this first model we have only two parameter, that is w1 plus w0 and w1. For this f2 predicted x, we have 1 2 3 4 5 5 number of parameters. So f2 model has more number of parameter than f1 model, so f2 model is more complex than our f1 model. So this is the thing. Okay, so option B is the right answer. So I think this is clear to all of you. Now let's move on to the next question. So we generate the data using the following model: y equals to 5x cube plus 2x plus x plus 3. So this is nothing but this is your true function. The f1 predicted x and f2 predicted x are your predicted function. Now true function is also given, that is y equals to 5x cube plus 2x plus x plus 3. So we fit the two model f1 predicted x and f2 predicted x on the this data, and train them using a neural network. So option A, f1 predicted x has a higher bias than f2 predicted x. F1 predicted has a higher variance than f2 predicted. F2 predicted has higher bias than f1 predicted, and f2 predicted has a higher variance than f1 predicted. So any guesses for this?
Oh, A and C. No, no.
A
Uh,
and C.
A and DD.
A and D. Okay. So any other guesses? Anyone else? Okay. So I have told you the simple trick. Also, you can remember the graph. This is the graph. Okay. This is the graph. This is the complexity. Let's say complexity by this, and this is the error. Okay. This is the error. So yeah. So thing is, as the model complexity is less, or let's say model complexity is less, we will have more bias, and we will have more bias and less variance. Okay, less variance. And as model complexity is high, we will have uh, low bias and more variance. Okay, so this is the equation. This is the equation. Okay, so this is the equation. Now we know that f2 predicted x is more complex than f1 predicted x. So f1 predicted x, as f1 predicted x is simpler model than f2 predicted x, f1 predicted x has higher bias than f2 predicted x. So option A is right. Now what about option B? F1 predicted x has higher variance than f2 predicted x. That cannot be true. F2 predicted x has higher bias than f1 predicted x. Again, this is false. And last, f2 predicted x has higher variance than f1 predicted x. Yeah, f2 predicted x is a complex model, so it will have higher bias and low variance. So option D is also correct. So option A and option D are correct. Okay. So this is the thing. This you always have to remember. Simpler the model, more will be the bias, less will be the variance. Complex the model, less will be the bias, more will be the variance. Okay. This is the thing. So is it clear to all of you?
Yes, sir. Yes, sir.
Now this is again a common question, but question number 3 and 4. Consider a function and its contour plot. So this is the function, this is the loss function, and it depends on two parameter, w and b, and your loss function is given by this: l equals to 0.5 w square plus 5b square plus 1. Yeah, and this is your contour plot, or this is your error plot. Okay, so the value here is shown. This is nothing but your loss. Okay, the one circle means same value of loss. Like this circle, the outermost circle means the value of loss is 2.4, and this inner circle 1.2 is the value of loss in this circle is 1.2. Okay, so this is the thing. Now what has been asked is, what is the sum of element of del L w star b star. So what is this W star B star? W star B star is nothing but your optimum value for which loss is minimum. Okay. So how you can calculate this? So for this you have to find what is the optimum value of W and B for which the loss is minimum. How we can do this? We can do this by nothing but our gradient descent. Okay. So let's do the gradient descent. So this is the gradient calculation. So first we will do del L by del W. Okay. And whenever we will do del L by del W, 0.5 into 2W, so that is 0.5 into 2W, that is W, okay, that is W. Now del L by del B you will do, and that is 5 into 2B, that is 10B. Okay, so del L by del B also you have done, that is 10B. So you have calculated del L by del W and del L by del B, that too you have calculated. Okay, now now the thing is yeah, now the thing is uh, what will be the value for which for the least loss, what will be the value for the gradient? For the least loss, the value of the gradient is 0. Okay, so for least loss, if I equate del L by del W equals to 0, so for that we will be getting W equals to 0, and this W is nothing but a W star. Okay, and whenever I will be equating del L by del B equals to 0, we will be getting B, and this B is again 0, and our B star is also 0. So W star is 0 and B star is also 0. Okay, and by that we can compute the least value of loss, that will be calculated when we put in this equation W star and B star, and that is 0, 0.5 into 0 and 5 into 0 plus 1. So our least loss will be equal to 1. That we are not interested. What we are interested in, finding this del L. Okay, so del L, how we can calculate del L? That is the sum of the elements. Okay, so sum of the elements for del L, that means we have to calculate nothing but del L by del W, and for del L by del W and del L by del B. At this condition, when both are 0, we have to calculate W star and B star, and we have to sum the element, that is W star plus B star. So at this equation, what is the value of W star and B star? That is 0. So 0 plus 0, our sum of element will be 0. So 0 is our answer. Okay, so this is the thing.
Sir, one doubt, sir.
Yeah,
So
please.
del L we are calculating here. Del L comma W comma B is equal to it is dou L by dou W at 0, dou L by dou W equal to 0, and dou L by dou B equal to 0. We have to add the both. The sum of elements you have given this one. How it comes actually? The del change in loss function del L is how it's related to the sum of these two.
Sum of this two.
No, you said no, this is del L is equal to dou L by dou W is equal to 0
Yeah, yeah,
plus dou L by dou B is equal to 0, which
yeah,
is 0 plus 0 is equal to 0. So
yeah.
how that relation comes? Yes, the L is lost. So
So you know this gradient descent, right? uh,
yes, sir.
for this gradient descent, we do the calculation in that way, right? This is our theta and this is our loss. Okay, so what is the del L by del theta is 0 at a optimum point. Whenever we will be solving this, del L by del theta equals to 0, we will be getting a optimum point, and that is nothing but our theta star, right? Because
Yeah, minimum.
at this point our gradient is not changing, right? Our gradient was earlier, what our gradient was earlier, y by x, right?
Negative.
Yeah,
Gradient was negative, then
negative,
it's
yeah,
positive.
negative, and then it is positive here.
Positive.
So
And
there
minimum
will
is
be
the
a point
constant.
at which our del L by del theta will be 0. Okay, and this
Uh,
point is nothing but the optimum point at which our loss will be minimum. So for
mm,
that only we have calculated the optimum point, that is W star and B star. Okay,
okay.
and so our minimum loss is coming 1. And then what we will do is, we will be taking this del L W star B star, so that is nothing but the your Yeah, that is nothing but this w star plus b star, okay, because at that point only our loss is 0, so w star plus b star will be equal to 0, okay. So 0 plus 0
Okay, sir.
equals to 0, so 0 is the answer, okay.
Okay, sir.
Okay, so let's, is it clear to all of you?
Oh,
Yeah, I think yeah. Now let's move on to the next thing. According to the eigenvalue of the Hessian, which parameter is the loss more sensitive? Okay, more sensitive to. So we have two parameter. One is W and another one is B. Now it is asking which parameter the loss is more sensitive to. Now how to do this question? This is a very interesting question. So for this we have to calculate this Hessian matrix. So what is this Hessian matrix? Hessian matrix is nothing but if we do the double differentiation of double differentiation of or if we do the double del if we apply a double del operator, we will get the Hessian matrix, okay. So earlier we are calculating del L by del W and del L by del B, okay. Now if we will do the do again put the gradient, and now our gradient would be del 2L by del W square and del sorry del B, this is del B, del 2L by del B2, and then we will have this del 2L by uh, uh, del 2L del by d by dw, if we will do so yeah, del 2L by del W del B and del 2L by del B del W. So this is the Hessian matrix. So you have to calculate the Hessian matrix first. So you will be calculating the Hessian matrix, that can be calculated. How this can be calculated? You just do this. You just do the double differentiation of this del L by del L by del L by del W you have calculated. Now again you do the del by del W. So what is the del L by del W? Del L by del W is this W, okay. Now again you do del L by del W to it, you will be getting 1. Del L by del B is 10 B. So if you will do this, it will be coming 10, okay. And then if you will do del by del B of this, what you will get is 0. If you will do del by del W of this, you will be getting 0, okay. So what are our elements now? Our elements are 1, 10 and this 0 and 0, okay. These are our elements, okay. This is the Hessian matrix. Now the thing with the Hessian matrix is this is a form of eigen value matrix, okay. So from this Hessian matrix we can get the eigenvalue matrix, as this is a diagonal matrix. So your diagonal elements are nothing but your eigenvalue, okay. So your eigenvalue of this matrix will be 1 and 10, okay. These are your eigenvalue. Now this one eigenvalue is associated with W, okay. This one eigenvalue is associated with W, and this 10 eigenvalue is associated with B, okay. Now we know that eigenvalue for eigenvalue parameter with more eigenvalue will be more the parameter which has more eigenvalue in this Hessian matrix, that will be more sensitive to loss than parameter with lesser value of lesser eigenvalue. So in this Hessian matrix we can clearly see that the W parameter is associated with one eigenvalue, and this B parameter is associated with eigenvalue 10. So that means B will be more sensitive to loss than W. So option A will be your correct answer, okay. So this is the thing. So is it clear to all of you what we have done? Hello, am I audible?
sir, yes, sir.
Yes, sir.
Where it comes, sir? Where it comes actually? We have discussed it in the slides now. Where this Asian matrix and all was not coming. In which method it is coming? Like
Oh, Hessian
uh,
matrix. This is a new thing, so we have not discussed in the theory part, but this is how you have to calculate. Okay.
okay, okay, okay. It's not with the discussed before.
No, no. This is how you have to calculate. Okay.
Okay, sir.
So
Okay,
let
okay,
me
okay.
summarize this two question. What exactly we have done? See, this is our contour plot. Okay. So this
Hmm.
contour plot, this is a equation of loss, and this loss is depending on two parameter w and b. And the equation of
Hmm.
loss was 0.5 w square plus 5b square plus 1. Okay, I think up
Hmm.
to this it is clear to all of you. And contour
Yes, sir.
plot, I
Yes.
hope everyone know how to observe this contour plot. In a contour plot, what happens is, for the same circle you will have same value of loss. Okay, so actually this thing is nothing but your 3D graph only. Your w and b, yeah, this is w. Okay, so it is not written, but this is w, this is b, and there will be a third axis where you will be getting the loss. But contour plot means you have cut the graph. Okay, that is why you have converted your 3D plot to a 2D plot. Now all the circle will have same value of loss. Okay, so that is about the question. Now first question, it was told is we have to find del L for this sum of elements for which this w star b star for del L. Okay, that you can have to find, that is only the sum of elements you have to find out, that is w star plus b star you have to find out for del L, or for that point for which gradient is
Hmm.
0. So that is the meaning of it. So how we will proceed it? For any such question, you have to first calculate the gradient. Okay, as we have two parameters, so we will calculate two gradient. Okay, one is del L by del W, and another one is del L by del B. Okay, so whenever we will be calculating del L by del W, that will be coming W, and whenever we will be calculating del L by del B, that is coming 10B. Okay, this is the thing about this, yeah, del L and del L by del W and del L by del B. Now to get the W star and B star, what you have to do is you have to equate this thing to 0. Whenever you will be equate this thing to 0, the point you will be getting is your W star and B star. So whenever you will equate w equals to 0, that point you will get is w star. So w star equals to 0. Similarly, whenever you will be equating this 10b equals to 0, you will be getting a b, that b is known as b star, and that will again be equal to 0. Now simply you can take the w star plus b star, and your answer will be coming this answer will be coming 0. Okay, that will be the question of the answer. Now another important thing I have just added is you can be told to compute the least loss. Okay, how you will compute it? You will just put the w star and b star in your equation. So whenever you will be putting the w star and b star in your equation, you will be getting the least loss, and that will be equal to zero point 0.5 into 0 plus 5 into 0 plus 1. That means the least loss or least loss will be 1. Okay, so that is the first question. Second question, the question was asking is, you have to find out that which parameter the loss is more sensitive to. So we have two parameter b and w, so we have to find out the loss is sensitive to which parameter. So for that we calculate this Hessian matrix. So what is this Hessian matrix? Earlier we have calculated is del L by del W and del L by del B. Now what we will do? We will do this del L by del W by del L by del W. Okay, del L by del W, and then d by dw to it. Okay, so that will be del
One.
2L by del W2. Okay, so that thing. Next thing is in this reason again you will be del L by del B we have calculated, and again we will do d by dB. So that will be d2L by d22. And in the diagonal, what we will calculate, earlier we have yeah, we have del L by del W, so now we will do d by dB. And here what we will do, earlier we have del L by del B, now d by dw. Okay, so by this we will calculate the Hessian
Okay, sorry,
matrix.
इससे देखिए तो बड़ा।
Ayan, I have one question,
Yeah, please.
please.
Yeah, please.
Actually, what is the use of this contour graph? We have loss we are calculating. Actually, I have the same question, but the L equation is different. But there is no use of this graph. Graph is
Yeah,
same in
yeah,
your
yeah,
question.
yeah. Graph, we don't have any use of graph. It is only
Use
shown
this.
here.
Okay.
Okay, only important thing is the equation. Okay, this equation
Okay.
is the main thing. This equation is the main thing.
Huh.
Contour plot
Yes,
is only
graph is
giving
same. for me, but the equation is different. There is no use of graph.
Yeah,
Yes.
graph there is no use, it is only shown for the data, it has no use, but this equation is the main thing. Okay, this is the main thing, this equation
Thank
is
you.
the main thing. Only if equation is also given to you, you could have solved the question, no problem. Okay, so this is the thing. Now the Hessian matrix you have to calculate, we already have del L by del W, you just do by dw to it and you will be getting 1, and you do del by del B to it and you will be getting 10, and these two diagonal elements you will be getting 0, because you are doing d by dv or del by del B for W, so this will also be 0, this will be also 0. So our matrix will be, Hessian matrix will be 1 0 0 10. Okay, and this is nothing but this is a these two elements are the eigenvalues
Again,
for your,
values.
yeah, for your Hessian matrix. Okay, because this is a diagonal matrix, and diagonal matrix means the diagonal only you will have elements, other elements is 0. So this is a diagonal matrix, and the elements of in the diagonal are nothing but your eigenvalues. Now this eigenvalue 1 is associated with the parameter w. Okay, and this 10 is associated with parameter b. So as the dominant eigenvalue is 10, so b will be more sensitive to this loss than your w. Okay, so this is the thing. So is it clear to all of you, these two questions?
Yes.
Okay, okay. Now question number 5, in the neural network, bagging is computationally expensive in terms of training, testing, both training and testing. Option D, none of the above.
I think C, sir.
Both training and testing. Okay.
Yes.
uh, Actually what happens is, yeah, C should be the right answer, C should be the right answer, so it will be for both training and testing. I think this is a mistake here, so C will be the right answer. So why it is computationally expensive? Because you are first taking the what I'm explaining. Yeah, you are first taking a bootstrap sample, and you will make different type of models to it. Okay, so then you will just train the model, and what will happen is, earlier you are training with only one model, so it is expensive for training. Now whenever you will apply a different test instance, now you have to apply that test instance to all the models separately, and then whatever the average prediction will be coming, that will be your test prediction. Okay, now so this so that is why this ensemble method is both in terms of bagging or anything, this is both computationally expensive in terms of both, that is training as well as testing. Okay, so C is the right answer. Okay, so yeah, there's a mistake here, so C is the right answer. Okay, so this is the thing. Now let's move on to the next question. We are training a neural network with the following patience parameter. Okay, this is a very important question of patience parameter. So when will the training stop? Okay, so yeah, let me just, yeah, so yeah, so now it is more clear. So when will be the training stop? So this is your table. So it has been asked when will be the training stop. The options that are given is after 5 epochs, after 4 epochs, after 6 epochs, and after 3 epochs. Okay, so any guesses for this? Am I audible?
Epoch 2, sir.
Can you please repeat? Can you please repeat?
After Epoch 3.
After
After Epoch 3, sir.
epoch 3.
Uh,
Okay, epoch 3 you are telling. Okay, epoch 3.
After epoch 5.
Yeah, epoch 5. Okay, yeah, so epoch 5 will be the answer, right? Epoch 3, how it is epoch 3? Epoch 3, okay, so you are telling that epoch 3 because your validation loss increases, right? So that is why you are telling epoch 3. So see, what does this early stopping? It monitors the validation error to determine when the training will stop. Patience 2. What does this patience 2 means? That is very important. Training will stop if the validation error does not improve for two consecutive epochs. So again I am telling, if the validation loss does not improve for two consecutive epochs, then you have to stop the training. Okay, now epoch 3, if you are telling epoch 3, you are telling the validation loss, if I after epoch 3 the validation error increases from 3.3 to 3.6. After epoch 5 the validation error does not improve after epoch 5, that is it remains 3.6, or it is lesser than 3.6. So since the patience is goes to 2, the training stop after 5. So why it is not after epoch 3? The epoch 3 training is in training validation loss is increasing, but you have to check for, as your patience is 2, so you have to check for two consecutive step. Okay, so two consecutive step you have to see. So 3.8, if we will see after 3.8, the it is decreasing for third epoch also, for fourth epoch also it is decreasing, right? Because if I compare from 3.8, it is decreasing for third epoch also, it is decreasing for fourth epoch also, but for fifth epoch it is not the same. Okay, after after 5 epoch it is not the same. Okay, so that is why you have to stop the training for after 5 epochs. Okay, so this is the thing. So again I am repeating, patience 2 means training stop if the validation error does not improve in two consecutive epochs. So you have to see the two consecutive epochs. Okay, and if the two consecutive epochs, if there is nothing happening, so you have to stop the training process. Okay, so that is the thing. So this after 4 it is remaining 3.6 only, that means it is remaining same and it does not improve, so that is why you have to stop the training at 5 epoch. Okay, so this is the thing. Okay, so you have to see that it
Okay.
is improving or not improving. So this is the thing. Okay, so let's move on to the next question. So suppose that a model produces zero training error. What happens if we use L2 regularization in general? It might increase training error, it might decrease test error, it might decrease the training error. Option D reduces the complexity of the model by driving less important weights to close to zero. Okay, so again repeating, suppose that model produces zero training error. Okay, model produces zero training error. What happens if we use the L2 regularization in general? It might increase the training error, it might decrease the test error, it might decrease the training error, reduces the complexity of the model by driving less important weight to close to zero. So any guesses for this?
D.
D. Okay, and why not A and B? A, B as well as D, right?
Complexity is reduced.
Yeah, but A also it might increase the training error, right? Because earlier our training error was L theta. Now it is L theta plus omega theta, right? Omega theta, right? L theta plus omega theta. So it increases the training error and it decreases the test error, because we are performing regularization, so it will perform better with the test data set. So option A is also right, option B is also right, and option D is also right. It might decrease the train error, that is not right. Okay, it will always increase your this training error. So this is the thing. So it will increase the training error, it might decrease the test error, it might decrease the training error, that is incorrect, and it will reduce the complexity of the model by driving the important weight close to zero. So this is the principle of regularization. So option A, B and D are correct. Okay, so is it clear to all of you? So suppose that okay, suppose that we apply dropout regularization to a feed forward neural network. Suppose further that mini batch gradient descent algorithm is used for updating the parameters of the network. Choose the correct statement. The dropout probability P can be different for each layer. Batch gradient descent cannot be used to update the parameters of the network. Option C, dropout with P equals to 0.5 act as an ensemble regularize. Okay. And option D, the weight of the neurons which were dropped during the forward propagation at pth iteration will not get updated at t plus 1th iteration. So any guesses for this?
So A and C.
Yeah, see the dropout probability P can be different for each layer. Yeah, absolutely right. Batch gradient descent cannot be used to update the parameters of
C,
the
sir. C.
network. So option B is, we are using mini batch gradient, right? Suppose that further mini batch gradient algorithm is used for updating the parameters. It cannot be used to update the parameter. Yeah, batch gradient descent can be used if we are not using mini batch gradient descent. Okay, so this, let's say this is false. Yeah, C is correct. The weight of the neurons which were dropped during the forward propagation at tth iteration will not get updated at t plus 1th iteration. Okay, the weight of the neuron which were dropped during the, yeah, t plus 1th iteration. Okay, but thing is, D can also be right, because whenever we are using dropout we are seeing in different types of neural network. Okay, different type of thin networks. So in one network it can be possible that the weights are dropped. In other network it can be possible that weights are not dropped. Okay, so I think that is why D should also be correct. So for me it is A, C and D, right? A, C and D will be the right answer, I think. Okay, D is not correct. Okay, okay, A and C. Okay, so yeah, D you can say, if we are talking about only one network, then D is iteration will not get, T is right. But if we are seeing for different type of neural network, different neural network, so what happens is, yeah, it is re-randomized, so it is false. So yeah, so option A and C are correct. D, it is the neuron which were dropped during the forward propagation at t iteration will not get updated at t plus 1th iteration. Okay, so yeah, so for one network, I think for one network, if we will see, if it is dropped for t iteration, it will not get updated for t plus 1 iteration. So for one network this is correct, but for many network if we will compare, so yeah, the dropout re-randomized, so that is why for many network it is incorrect. So C, D, if we are talking about many network only, then it is incorrect. If we are talking about one network, this is correct. So I think A, C and D according to me is right. Okay, so this is the thing. So has everyone got it what I was telling?
Yes, sir.
Okay. Now this is the question. We have trained four different models on the same dataset using various hyperparameter. The training and validation error for each model are provided below. This is the thing. Based on the information, which model is likely to perform best on the test dataset. Okay, so model 1, this is the training and validation error for model 1. Model 2, train and validation error 3 and 4. Okay, so any guesses for this?
Model 4.
Model 4. Okay,
4, sir.
okay.
Model 2.
Yeah, model 2. Yeah, I think model 2 is more accurate, right? Because model 4, if you say, the training and test error both are very high. Okay, model 2 training and test error is means less. Model 3 test error is less, but training error is more, so that means it is underfit. Okay, model is underfit here. First, if you will see, the training error is less, test error is more, so overfitting is here. Here also some kind of overfitting is here, but this is acceptable because both the training error and validation error is less. Last model training error validation error is very high for both the this training and for this training and validation error is high for the fourth model. So that is why second is most appropriate. Okay, so let's see model training error. Yeah, so yeah, first is the overfitting case that I have told you. Second, very low training and low validation error, so good generalization. Yeah, so model 3, high training error but very low validation error, so this is underfitting. Fourth, both the error are very high, so this is clear case of severe underfitting, because the model is not fitting neither in training nor in testing. We cannot expect in testing, so that is why model 4, this is the model 4, so option B is the right answer. Okay, best choice is B. Okay, so is it clear for why I am
Yes, sir.
telling B? Because it has low training and validation error, minimum overfitting, underfitting, likely to perform well on test dataset based on the test error. Okay, test error is ideally less in this zero point 0.5, that is model 3, but here we are not taking the model 3, because here it is a clear case of underfitting, because training error here is very large, so this is the problem here. Okay, bias is higher because training error is directly related to this high bias, so as it is a clear case of underfitting, so that is why it will have high bias. Okay, so option B is the right answer. Okay, so let's move on to the last question. Consider the problem of recognizing an alphabet in uppercase or lowercase of English language in an image. There are 26 alphabets in the language. Therefore, the team decided to use CNN network to solve the problem. Suppose the data augmentation technique is being used for regularization. Then, which of the following transformation on the training images is are appropriate to the problem? Option A, rotating the image by plus minus 10 degree. Option B, rotating the images by plus minus 180 degree. Option C, translating the image by 1 pixel in all direction. Option D, cropping. So any guesses for
A,
this?
A, B, C.
Yes, sir, ABC.
A, B, C, not D.
Yes, sir. Cropping will remove some of the information, no, sir.
Yeah, but cropping can be used. B cannot be used.
Oh,
Why B cannot be used?
it is
Let's say W is the alphabet. Now uh, uh, W is this is 90-degree rotation, 90 degree. This is the DA, and yeah, this and this. Okay. So this is 90-degree rotation, and 180-degree rotation will be 180-degree rotation will be this, right? So W has been changed to M. Okay, remember whenever we were discussing this thing, augmentation, dataset augmentation, what is that? The dataset augmentation, yeah, this is the dataset augmentation. What we have focused on majorly, we exploit the fact that certain transformation on the image do not change the label of the image, but whenever you will do this 180-degree augmentation, what will happen is it will change the label of the image. The W can be changed to M, like that. There are some alphabet like, yeah, D could be changed to P, etc, etc. So this is the thing, so that is why you cannot use this B. Cropping, see, cropping, yeah, you are right in some cases, like this W is written, now you cannot crop like this. Okay, you cannot crop like this, that will not understand the true level. But like this W is written in this amount of page, and now you are cropping to this, so this is acceptable. So that is why cropping in some cases is still appropriate if done carefully. Again, this is the warning sign that if it is done carefully, it is appropriate. But this 180-degree rotation cannot be done. 10 degree okay chalega, but 180 degree cannot be done. Okay, translating the image by 1 pixel in all direction, that this can also be done, but cropping can also be done, but this 180 degree rotation of images cannot be done. Okay, so option A, C and D are correct answer. Okay, so this is the thing. Okay. Okay, so by this I am ending the session for today. Any more doubt?
Sir, how
Okay,
to
and
prepare for the exam, sir?
prepare for the
Yes,
exam.
sir.
Exam question will be very similar like your assignment questions. Okay, so if you will do your assignment question properly each week, so you are already
Ah,
prepared for your exam, and also the content or the questions provided by TA. So this two set of question, if you can done the questions that are provided by us as well as the assignment question, so you will be well prepared for the exam. Okay.
sir, I am doing for my PhD coursework here, this one.
Okay.
So I have to score a very high mark for this. Then only
Yeah,
they are
yeah.
issued.
I think if your concepts are clear, you can answer any question.
Sometimes the question goes to nook and corner where I can't answer some of the things like this and all. We have seen that image, but now if you understand in a very practical manner, then we can answer this question.
Yeah, yeah.
So
So
it's like
yeah, this MCQ questions are always tricky, and whenever you have multiple choice MCQ question, these are more tricky because you can miss some questions or
yeah, it is.
miss some options, or either you can make one two option, means you can guess one two option wrong. So this is always a
Hmm.
trouble whenever we are dealing with MCQ. But otherwise, another important thing in NPTEL is you don't have any negative marking, so this is a positive point. So that is the thing.
Okay, sir.
So
Hmm.
you can, I think, score well if you will be doing the assignment question properly
Things.
and the question that we are providing. Okay, these questions
Okay,
are
sir.
also very similar to assignment only. So that is only our
Okay, sir.
duties, that to
Hmm.
make you understand question that will be similar to your assignments. Okay, so these two sets of
Okay, sir.
questions if you will do, so you will score well. And another
Thank you, sir.
important thing is regarding the codes. Again I have okay, where is the thing? Yeah. Again I have made you prepared some of the codes for this yeah, again I have prepared some of the codes for this week, like some of the codes like augmentation for regularization, this you can see, and some of the codes like train versus test error, etc, etc. So this codes you can open, you can just copy to your drive and you can run it and you can see the results of it. Codes, it is not possible to discuss codes because of this limited time, but what I am doing is I am providing you the code in this DL code folder. So you just open the folder,
Use it. Yeah.
yeah, copy the code to your drive and you can run it. Okay, and you can change the
Okay, sir.
parameters. So at least by this you should understand how to the manner in which code could be written. If you understand the manner, then you can just modify your things and etc, and
Parameters.
yeah, parameters, and you can see different set of results. Okay, so
Okay, sir.
this is all about today's lecture. Okay.
Okay, sir. Thank you.
Okay, so by this I am ending the session for today. We will meet on the next Tuesday. Okay.
Thank you, sir. Thank you.
Okay.
Thank you, sir.
Thank you, sir.